move to the last speaker of the session, who is Lorenzo Monacelli from the University of Rome, that will talk about dynamic propagation of quantum nuclei.
Oh, okay, so yes, the microphone is working. Is it okay? Okay. So, first of all, I want to thank the organizer for inviting me here in this beautiful city and to give me the opportunity to tell you about the quantum effects on nuclei and how to efficiently account them in your simulation. So, my presentation is divided into two parts. In the first part, I will describe the numerical tool that can be used to assess the quantum nature of nuclei, and then in the second part I will present a test case, a very interesting test case that is high pressure hydrogen, in which quantum nuclear effect completely change all the physical properties. So, what are quantum effects on nuclei? In a standard simulation, you usually treat the nuclei as fixed dimensionless points. However, indeed, they have a wave function, and this can alter the properties of the system you are studying. So in particular, we would like to have a tool that is able to grasp the ground state nuclear wave function and also all the equilibrium nuclear density matrix if we are at finite temperature that encodes for all statical properties of the system and the thermodynamical properties. Then indeed, we would also be able to study how this wave function can respond to dynamic perturbations. That is what happens in usual experiments like vibrational spectroscopy, Raman or infrared vibrational spectroscopy, neutron scattering, and so on, so on. So we would like to be able to describe them, indeed. And last but not least, nowadays, you know, pan-probe experiments are becoming very important, and so we would also be able to have tools that allow us to simulate the time-dependent propagation of the nuclear wave function even far from equilibrium. So we develop a tool to do all this, that is the time-dependent self-consistent harmonic approximation that I'm going to introduce in the next slides. So let's start from the statical problem. So we want to describe statical properties. I will describe it at t equals 0. That is easier, but it applies also at finite temperature. So the ground state nuclear wave function in the Born-Oppenheimer approximation can be obtained by the least energy principle that states that the exact wave function is the one that minimizes the energy obtained as the average of the Hamiltonian. So we are within Born-Oppenheimer approximation in the whole talk, and this Hamiltonian can be divided into ionic kinetic energy plus the Born-Oppenheimer energy potential that encodes for electrons, indeed. Up to now, everything is exact within Born-Oppenheimer. So our approximation is we restrict all possible wave function just to the most general multidimensional Gaussian. So this very ugly equation is just a Gaussian in multidimension. And so we have two kinds of degrees of freedom here that are these R, that are the average position of the atoms inside the lattice, and this upsilon matrix here that encodes for quantum fluctuation, that is the width of our Gaussians. So it is called a self-consistent harmonic approximation because a Gaussian is always ground state of an harmonic Hamiltonian. So our wave function somehow satisfies all possible sum rule because it's the physical solution of a real problem, not the one we want to study, but there exists a real problem through which our wave function is solution to. So this is t equals 0, as I anticipated. However, it's very trivial to extend this at finite temperature. We just need to add entropy here, and so we must minimize the free energy, not the energy, and to replace a Gaussian wave function with a Gaussian density matrix. So it's just technical, but it can be done at finite temperature as well. So why do we use Gaussians? Gaussians are very important because we have a limited number of degrees of freedom, so we do not need any basis set, any truncation error. We can describe a Gaussian with few parameters. And the kinetic energy, and if we are at finite temperature, the entropy of a Gaussian are known analytically. So we do not have to compute kinetic energy on entropy by doing some complex path integral approach or something like, or thermodynamic integral approach. And the only part that remains to be computed actually numerically is the potential energy. So what actually we do, we generate ionic randomly displaced configuration according to our Gaussian wave function. That is very easy. We compute the ground state electronic energy using a DFT code, for example, or more sophisticated technique. And then we average them, and we obtain, with the kinetic energy and the entropy, the free energy of the system, and then we minimize it with respect to our parameters. So it is computationally cheap. It's of the same of complexity of a standard Born-Oppenheimer molecular dynamics, but it includes quantum effects on nuclei, indeed. So let's start with a simple one-dimensional example to have a bit of idea of what's happening. I take a very anharmonic and ugly Born-Oppenheimer, let's call it energy landscape for one particle in one dimension, and we can try to solve this numerically exactly, at least at the numerical precision, with an exact diagonalization, and this is the result. So this point on the x-axis is the average position of our exact, in principle, wave function, and on the y-axis we have the ground state energy. So as you can see, this is a very highly anharmonic system. Okay, so our average position is not in the minimum because of quantum fluctuations. We can use a standard technique that is quasi-harmonic approximation, and in this case it fails dramatically because quasi-harmonic approximation means we solve the system as it is a classical system, so we find the global minimum of our landscape, that is here. Okay, and then on this point we add the energy of the harmonic oscillator that we would obtain by expanding up to second order the potential around this point. And here you see we get a very not so good value of energy and not so good value of the position indeed. We can look for self-consistent harmonic approximation and we get this point here. So it's very good for describing anharmonic systems, even when quantum effects are very important. We can have a look at the wave functions. So in black, we have the exact wave function here, and as you can see, it is not a Gaussian. Indeed, it is not an harmonic oscillator, while the red dashed line is our wave function. That is placed well in space, but indeed the exact shape is not correct. So message, the core message for this is energy and its derivatives that are all thermodynamically important quantities likely are very well described by self-consistent harmonic approximation, even in an harmonic system, while the wave function is not so well. And this is a consequence of the variational principle, if you want. So this is to describe static properties. Now we want also to be able to describe dynamical properties. For example, they respond to time-dependent perturbations. And to do this, we need to include a time dependency in our wave function. So we need to reformulate the theory in a time-dependent way. How can we do that? So instead choosing the wave function that minimizes energy, we choose the wave function that makes the Dirac action stationary along its path. This is somehow equivalent on what is done in time-dependent DFT or time-dependent RT-FOC. So this is the Dirac action, and we do exactly the same ansatz as for the static one, so we take the most general Gaussian, but this time the parameters indeed depends on time and must be also complex, otherwise it does not couple with the time derivative here. So we can see, if it works, an example of this dynamical. We have the Born-Oppenheimer surface time-dependent evolves here. This is the exact wave function evolution, and this is the time-dependent self-consistent harmonic approximation. Here we can see the average position in the two, in the approximation and in the exact solution. So the red dashed lines is our approximation. As you can see, this one is not a Gaussian during the evolution, while the time-dependent self-consistent harmonic approximation remains a Gaussian. But the time evolution is actually very well, even in this case, in which, in principle, it is not. Indeed, here deviates a bit, but not so much. And we can use these dynamical effects to compute, for example, correlation function of the position that are those that are measured in an infrared spectroscopy experiment or a Raman spectroscopy experiment. And we can do that in this case. And you can see this is what we would obtain, for example, in a harmonic approximation. This is equivalent of a Raman experiment, a virtual Raman experiment on our system. This red dashed line is what we obtain with the time-dependent self-consistent harmonic approximation, while the black one is the exact result. So if you have an harmonic system and you want to study, for example, vibrational properties and compare with experiments, then this tool, even in highly anharmonic system like this one, will give a very good result, even when harmonic theory fades dramatically. So I hope I convince you about how this theory works in a very easy system. It is one-dimensional. But now let's see a much more complex system made by many atoms in the cell, and let's see how it works. So why I study high-pressure hydrogen? This is a very important and a very interesting system because it is predicted to be a room temperature superconductor, at least its atomic metallic state. And this hope to have a room temperature superconductor was recently confirmed somehow by the discovery of hydrates like H3S or lanthanum H10, in which we almost got room temperature superconductivity. So it's a field that its importance is increasing in these years. And however, the challenge of getting the atomic metallic state of hydrogen is a bit more difficult than one was expected in origin, because the original prediction was 25 GPa of hydrogen metallization, and this revealed to be wrong. Probably it's about 500 GPa, so a bit more challenging. And the reason is that hydrogen at high pressure has a very complex phase diagram. You can see many phases, and these are all molecular phases in which we have still the hydrogen molecule inside. And to make things more difficult, we have very few experimental probes that can be used on hydrogen. So some of these phases are still very highly debated in literature, so we do not know if they exist or not. And the reason is that, as I was anticipating, is that hydrogen is a very challenging material. It has one electron. This means that X-ray, that is the crystallography, the most important experimental technique to see crystallographic data, is very difficult to be done explicitly at high pressure, where the sample is also very small. And neutron that should have a high cross-section, but cannot be applied when the sample is too small, like the one in the diamond anvil cell for high pressure at room temperature. Not only, hydrogen has one electron. This means that it is very easy for us to simulate, but it has also one proton, so quantum effect will be very important. To give you a number, the Heisenberg uncertainty on the position of one atom inside one molecule is about 10% of the H2 bond length, so it's really huge. And so the only experimental tools that we have to study these phase diagrams are optical properties, so transmittance, reflectivity, and vibrational spectroscopy. So let's start with the results I obtain. I will start with statical results that cannot be experimentally, somehow are difficult to be experimentally discovered. So this is the candidate starter for phase 3. Phase 3 is one of the most important phases. It is at high pressure, so above 150 GPa at low temperature. And as you can see, it's a mess. So it's made by layers. It has a lot of atoms, 24 atoms in a unit cell. It's made by layers, and each layer has this molecule arranged in this kind of rings. I colored these rings just to give you an idea on how they are disposed in space. Otherwise, it's really difficult to see, because it is something like a disordered system, okay? And so we can study how the structure of this material change when we include quantum effects on nuclei. So this is the average bond length of one molecule as a function of pressure. So as you can see, if we use static nuclei, so without quantum effects, we have something that is almost completely flat. And this is quite reasonable, because this is a molecular crystal, so it's made by molecule, and when we apply pressure, the molecule just get closer, but the single molecule is not so much affected by the pressure. Otherwise, when we include the quantum effects on nuclei, you can see that the average distance between the two atoms inside a molecule increases. And so this is a sign of molecular dissociation, and it's because there is as molecules get closer while increasing pressure, there is tunneling between one molecule and another, and each atom can form a bond with the atom of the other molecule, and so start tunneling between two molecules. And so this is a pure quantum effects, okay? You can see here. And this has strong consequences, indeed, in the experimental observable, because the bond length is changing a lot with pressure. We can also see how the equation of state is modified by quantum effects. Here, the effect is much less impressive than in the previous slide. However, at fixed pressure, the volume increases by about, this is t equals 0, by about 1.3%. That is not neglectable. And this effect is non-isotropical, because if we look at the ratio between the distance between two planes and the typical distance between inside a single plane of molecules, we see that this increases. So this means, with respect to the static one, here also it changed slope. So this means that quantum effects are trying to pushing away the planes of our system. So, but up to now, it's all speculation, because all these parameters cannot be seen experimentally, so this is just some mind work. Because the only thing, the most important kind of experiment that can be done on this system are vibrational spectroscopy. And so this is a typical Raman-run, an experimental Raman-run, in which they see different phase transition through the appearance of new peak or changes in the slope. So this kind of experiment is almost only what we have on the structure of this kind of material. So we must try to reproduce this experiment. And I did this. This is infrared vibrational spectroscopy and Raman vibrational spectroscopy. I focused here on the vibron, that is the most intense infrared and Raman activity on this molecule. And as you can see, here we have harmonic approximation in blue, and in black we have our results with the time-dependent self-consistent harmonic approximation. In red we have experiments. As you can see, the renormalization of the vibrational frequency here is 1,000 centimeters to the -1. That is 25%. It's really a lot, okay, with respect to harmonic. And we get much closer also for the slope to the experimental data. Not only, we have also dynamical effects. So, for example, if you look at the Raman, as we increase the pressure, we can reproduce very well the increase of the full width of the vibron, that is the lifetime, the finite lifetime that this phonon mode acquires due to phonon-phonon scattering, to an harmonic phonon-phonon scattering. So, to conclude the last part of the talk, I will talk you about the optical properties that maybe are the most impressive result on hydrogen and to electron phonon coupling. So this is the experimental picture on optical properties of this phase of hydrogen. That is, I have to say, quite strange. So there are three main kind of experiments that have been done on this phase, and they seem to say completely different things. So if one look at reflectivity in visible light, one sees that this phase is transparent up to 320, more or less, GPa, and then it becomes black. It remains black for a very long time, up to 419, and here there is an experiment that is very debated, I have to say, but in which they claim that this phase becomes shiny in the visible light. So they say this is a metal transition, and they reach atomic metallic state at this pressure. Then this year, Eremet's group published a work in which he measured conductivity on hydrogen, and he says that hydrogen remains in the same phase, insulator up to 360, and then it starts conducing electricity. And you see here that there seems to be a contradiction. So this is a black metal. What is this? And then if you look at, there is another experiment that makes things still more confusing, in my opinion, that was done by Lobert. I know it has been accepted on Nature now, and in which he measured the transmittance in the near infrared. And he sees that it remains transparent up to 420 GPa, where it suddenly becomes opaque. So each one of these experiments claims that metallization is reached at different pressure. So you can see it's a mess. And indeed, in this region, something really strange seems to happen. So it is black, if all the experiments are correct. It is black, in the infrared is transparent, and it conduces electricity. Something really strange. So we can simulate this behavior. So how it is done? It is done in the supercell approach, like the one Professor Gons described in the previous talks, in which we generate a very large supercell of this system, and with atoms displaced according to our anharmonic wave function, Gaussian wave function. And then we compute all optical properties from this very large supercell. So at first, these are a comparison with the clean case, so without phonons, so with the atoms fixed in their ideal position. And these two lines are with phonons generated in two different supercells, one of 96 atoms and the other of 432 atoms. So the first thing you can notice is that this is the density of state as a function of energy. As you can notice, the indirect gap closes by 2 electron volts when we include quantum effects. So you cannot. So if you don't consider electron phonon here, you will completely miss the correct description of hydrogen. And the other thing that you can observe is that there is a huge size effect. In practice, close to metallization. In fact, if you use a small cell to generate your system, like it is done usually if you use path integral or something like that, you cannot simulate very large cell. But we can, because we can interpolate a Gaussian to a virtually infinite supercell. You see here that the density of state close to the Fermi energy strongly depends on the cell size effect. And indeed, also here you will miss the correct the determination if it is a metal or not. So let's go to the results. And here I resume all the results we obtained on hydrogen. So you can see here we have the density of states similar to what I showed in the previous one. And we can see for 3 pressure, 260, 355, and 460 GPa. And we can see that the gap is open and closes somewhere between 355 and 460 GPa. So we would, if here these square dots are the indirect gap measured from the density of state, and you can see if we trace a line that this transition occurs at about 380 GPa. And so we predict that there is an onset in the static conductivity at about 380 at 0 Kelvin. That is in quite good agreement to the Hermet's paper that I remember he says that he sees this sample to conduce electricity at 360 GPa. On the other, we can simulate also optical properties to see the color, for example. And we can see that at 260 GPa, this is the transmittance light, and it drops down above 3 electron volt. This is the visible light. 3 electron volt is here. So it means that at 260 it is transparent. At 355, it starts absorbing at above 1.5 almost electron volt. That is here. So at 355 is black. So this phase becomes black somewhere, and the reflectivity is very low. And so it becomes black somewhere between 355 and 260. That is in very good agreement with the experiment. And we can map this optical gap that is as it is measured by experiment, because experimentally they can see only transmittance. So in the infrared, these are the data of Lobert paper. And as you can see, these are our data are in very good agreement with the experiments. So we can reproduce the optical conductivity. Moreover, even after the optical gap is closed, so the system should be a reasonably quite good metal. The reflectivity is completely flat, and below 20%. This means it will appear black. So this system is a very exotic behavior. It's a black metal, and in this region of pressure, it will be transparent in the infrared. So we are able to reproduce exactly all the properties of this hydrogen by explicitly accounting for quantum effects. I want you to notice here these open symbols, black open symbols, are the results without quantum effects. So you can see that they are completely off. In this case, optical gap closes by 3 electron volt when you add the quantum effects on nuclei. We are at T equals 0. And indeed, we can try to substitute hydrogen with deuterium, and we have these red points here. And so the gap shift between hydrogen and deuterium of 1.2 electron volt. So this is a really huge result, isotope shift. I think that no material has such a strong isotope shift on the band structure as hydrogen. And and this is a prediction, so we are waiting for, Lobert claims to have experiments on deuterium, so we are waiting for them to see if we overlap or not. And so, for my conclusions, this self-consistent harmonic approximation can study systems in which quantum effects may reshape the structure, phonon energy, lifetimes, and alter all electronic properties. And this is explicitly important if you study a system with light atoms, and hydrogen is the lightest atom of all. And it can be used to simulate all these effects. So we have an open source code that I hope we will release very soon, and we are working now on the release. So stay tuned if you and so you will be able to apply all this stuff easily to your favorite system. So thank you for the attention.
Thank you very much, Lorenzo, for the talk. So we have some time for discussion. Any question from the audience?
So in the insulating phase related to my talk, there is some infrared activity, but because everything is hydrogen, I guess that the infrared activity is quite small, although you mentioned that the vibron had a large infrared activity. What is the Born effective charge then?
Okay, so I don't remember exactly the number. So it's not neglectable, and in particular, So in particular, here the whole line width is not explained by phonon-phonon scattering, but it is an electrostatic effect. So it's the fact that the electric constant becomes negative, and at the and then it becomes again positive between LO and TO frequency. So this is not a neglectable effect here. So effective charge in this particular phase, so hydrogen shouldn't have, but this phase has this.
Well, it depends on the symmetry breaking.
Yeah.
There are indeed some, as soon as you have 4 atoms in a unit cell, you can have indeed small Born effective charge, but I would have liked to, even 3, selenium, tellurium. Okay, well, it would be interesting to know this number that should be small, and anyhow, it will not be comparable with oxygen.
No, I don't think so. No, I don't
in metal oxide.
No, I don't think.
Yeah. Okay.
When you mention gap, which gap is that? Is density functional or?
Okay, yeah. So all the data here, I obtained them using the modified Baylor-Johnson functional, exchange correlation functional, that in this case we tested it against HSE06, and it gives a very good result. So this is a meta-GGA functional that has been developed explicitly to study the band structure, and it is one of the best functional to, as far as we know, to get electronic properties. So here, all the calculation, all the self-consistent harmonic approximation is done with the BLIP, with density functional theory, and then the electronic properties are computed in this randomly displaced nuclear configuration with this modified Baylor-Johnson. It is implemented also in Quantum Espresso as TB09. I don't know if you are familiar with this.
Yes, maybe you already explained, but I'm a bit confused with the name of the approximation. So I guess harmonic comes from the fact that you are using Gaussians,
Yeah.
but then self-consistent.
Okay.
Are the electrons feeling these quantum effects from the ions in your case, or?
No, all the electronic in this theory up to now. So I'm starting thinking about how breaking the Born-Oppenheimer approximation,
Okay.
but everything now is done at
Everything is
Born-Oppenheimer.
Born-Oppenheimer.
So electrons are present in this term here. That is the Born-Oppenheimer. So in practice, what we do to simulate these things is we generate this randomly displaced ionic configuration according to this wave function. And then for each one of these, we compute a total energy calculation with a DFT code, for example.
Okay.
So here, and then this average is done averaging all that total energy that comes from a DFT calculation.
Okay.
So that's how we include electronic properties in electronic energy, so electrons are treated with wave function at the level of DFT, in this case of hydrogen. In principle, here you can substitute DFT with any technique
I
you
see.
want.
Thank you.
Do we have any other question from the audience?
How sure are people about the structure of hydrogen? of this
That's
pressure?
another good question. Okay.
Did somebody make the structure prediction calculations already?
Yeah. I have not said this. So this structure has been predicted by Chris Pickard group, and so now, since I told you that there are very few experimental signature, one must compare with Raman and optical properties if one want to compare with experiments. There are many structures that are very close in enthalpy, about a few milli-electron volt per atoms, so it's really difficult to reach the correct DFT accuracy. So the DFT accuracy cannot be sufficient there to disentangle which one is the ground state. Indeed, there are quantum effects that need to be taken into account, and this means that it's somehow not trivial from simulation. So the best thing is taking the few candidates. This is one, and this is probably the best one, explicitly for the high pressure part, above 250 GPa is probably that one. And we tested it, so this Raman calculation was also meant to test this structure, actually. And you can see, if you take harmonic results, they are not so good as a prediction. Instead, if you, especially above 250, they are very good. Here still there is an offset of 200 centimeters to the -1. This is neglectable between this one here, but still there is an offset here. I believe this offset is related to DFT accuracy. And the reason is that if you, for example, do an harmonic calculation with BLIP or PBE, you get differences of 800 centimeters to the -1. So there is also DFT error in this. So I believe this is still DFT error, not an harmonic stuff. But indeed, the fact that we increase a lot the agreement with the experiment, we are also able to predict correctly the vibron full width as a function of pressure, and the fact that we reproduce exactly this very strange behavior of black metal, metallic hydrogen. I believe this is a proof that this structure is actually the correct one for phase 3.
Thank you.
Somehow.
We have time for the last question. If not, let's thank Lorenzo again for the nice talk and discussion. And it's time for the coffee break. So the coffee break is just, I think we need to exit and enter in the room just nearby here. It's just here. Thank you.